Hi everyone, my name is Guillaume Lambert. Today I'm going to tell you about a product I'm working with in collaboration with Advanced Blockchain. We call it Panoptic. And this is based on the title of my talk. We're creating a perpetual option primitive based on Uniswap v3. And just to lay it out, I'm giving you the executive summary of what Panoptic is. First, in Panoptic, options are created by relocating liquidity within any UniV3 pool. So any UniV3 pool that exists, you could create an option on top of it, ETH DAI, ETH USDC, or ETH Ribbon, whichever token you want. Pricing itself is also a problem that we solve where pricing is path dependent. And unlike regular options, the price of an option starts at 0 and goes up, as opposed to being fixed and maybe going down. And finally, we're bringing back fungible liquidity to UniV3. So liquidity providers or market makers will be able to provide liquidity at any ratio, at any range in the pool, and the users will be the one that will be handling the liquidity relocation. And this is the brief outline of the talk. Just before also going forward, thanks very much, Alexis, for describing options. I realized I didn't cover this super well, and hopefully now you know everything about options, so it's going to be much easier to explain. And one question is why trade options? And I personally trade options, and as Alexis said, you can buy options, but I find it more interesting to sell them. You can sell them because that allows you to control your delta a little bit more. We all know about delta neutral strategies. These are strategies that are resilient to price fluctuations. You can have a swing of 10, 20%. Your capital doesn't decrease as much. You can have negative delta. This is similar to shorting. You can buy a put. If the price goes down, you profit more. You can also be positive delta, but you can also do it in any funky way. As you can see here, the profit zones are in green. The loss zones are in red. But in the end, you can create any type of payoff curve you want. And then for a more deeper point of view, it's very easy to understand options from the math perspective. You can understand the expected move, the probability of profit of any option you create. You can also be a lot more capital efficient. If you were to trade options on the traditional exchange or TradFi exchange, you can be from 2x to 15x more capital efficient than buying the asset or the stock outright. And finally, I hinted at that. What I like the most about options is that you can create any type of payoff you want. They can be very simple, like a straddle or a strangle, or they can be very funky, like a bat signal or a zebra. I have a saying, why buy a stock when you can create a zebra for a fifth of the price? And this is true. All of these options may be complex. They may contain 1, 2, 3, even 6 legs, but overall, they allow you to be a lot more nimble and capital efficient. So first, let's describe how we implement options in Panoptic. So for those that know Uniswap v3, Uniswap v3 allowed users to deploy liquidity at specific ranges. So it's not full range from 0 to infinity like Uniswap v2, but rather you can specify which range you want to use. A key point is that if the price leaves the range, if the price goes below the lower limit, your 100% ETH, for instance, in an ETH DAI pool, if your price is above the upper tick, you're 100% DAI. So you only accrue fees when you're within that range. And the payoff kind of looks like a straight line here if it's below, and then it plateaus and is constant as the price keeps on increasing. And again, this is something that I've written about somewhat, but this is very similar to a covered call option. The payoff is very similar. You have a region where it's flat, where it's just cash that you're holding, a region where it's a slope at 45 degrees that tells you have a stock holding. So the link between the payoff curves of UniV3 LP positions and those of a covered call were enough to kind of entice me and do a little bit more research on that. So if you go out right now, launch UniV3, you can supply liquidity. And if the liquidity is supplied below the current price, you'll be creating a short put. You would be selling a put. And this is what the payoff you would like. You have a large likelihood of losing, a good likelihood of winning, but you won't win much. The amount that you win will be, or your positive is your fees that you are accumulating. So overall, this is something you can do right now in a decentralized manner. You can sell puts in any pool. But what's interesting and what people want to be able to do is buying options. What about buying a put? So naively, you can think of buying a put as an insurance policy that if, say, there's a protocol hack or a rug pull, some market collapse or some dubious tokenomics, you maybe want to be protected on the downside so that when the price collapses, you'll be benefiting. So one naive way of thinking about this, maybe you do the opposite of a short put. Instead of supplying liquidity, you borrow it or you remove it from the pool. And if you look at the payoff curve of removing liquidity, you would have exactly the mirror image, I guess the flip on the along the y-axis. And if you were to do that, that's it, that's fine. You would have to create exchanges, you would have to manage liquidations, and overall you have to trust the users to pay back what they borrowed. You don't want to have the protocol be left out with bad debt. So having and trusting that fund to the user causes some problems. So one solution we came up with is not even give it to the user, but then assign it to them. So what happens is that when you purchase a put, you remove liquidity, but you store it within the Uniswap v3 smart contract, but you store it at the minimum tick that's available. So this one is 10 to the negative 30. It's never going to reach that price, but it's there. It's ready to be used or moved back if need be, so that whenever it's time to exercise, the user will just have to interact with the smart contract and say, okay, I want to exercise my put. I just have to relocate that liquidity either to the strike or to some other way, some other places. So I'm going to walk through what happens concretely when you buy a put and store liquidity at the minimum tick. First, you borrow liquidity at a strike K. You move it back to negative and to zero, basically, in price. And then you hold it. This is a perpetual option. There's no expiration. You just hold it for as long as you want. And at the end of the day, if the price is still above your strike, you just take the DAI that you moved there, pay back the debt that you incurred, no profit, no loss really, except you may have collected some fee. You may have to pay some fees afterward. I'll describe this. And this is kind of the borrowing alternative. If instead the price goes down and crosses that little debt well, the debt which used to be KDAI will become 1 ETH exactly. So the user is entitled to get back the KDAI that they stored at zero, and at the time of exercise, they keep this KDAI, they supply 1 ETH, so effectively they sell 1 ETH for KDAI, regardless of the price of ETH currently. And since they can buy 1 ETH much lower in price than K, the actual profit is K minus S. And you actually recover this exact payoff curve. So here the key point is that you can store the liquidity in the pool and just have the users move it back and forth without really accessing it. And they make the profit by just selling it at a fixed price regardless of the current price of ETH. And you can be a bit more general in the way you create those. You can have a wider liquidity that you borrow. You put it to plus infinity, bring it back. You can have cap payoff. You can have something that's a little bit smoother here. This is actually limiting gamma of your option. Typically, when you have a regular option, as you approach expiry, there's a gamma risk, or you can actually have a gamma explosion where you can be very sensitive to small price moves. Here, by widening your option, you can be a little bit more resilient. And again, this is something I've been kind of writing about, and overall, as long as you can move liquidity, so that means that the Panoptic protocol will have to own and manage that liquidity, but that the users will have access to that liquidity. They could create any payoff they want. So that's how you can create the green regions, the red regions, of just moving liquidity at different locations. One key point is the price. How do you price those instruments? And again, we were thinking about that for a long time. We came up to that Oracle-less Black-Scholes pricing. So Black-Scholes is kind of the standard state-of-the-art way of pricing options. But just before we go there, let's look at how fees are collected in a position. So you have a user that deploys liquidity at a fixed range that's above the current price, for instance. Sometimes the price, these are simulations, but the price may never touch the point where you deploy liquidity. You collect zero fee, even though you stayed in the position for months. Sometimes it does cross, but then it leaves it far away, so you collect a slight amount of fee. And then the sweet spot is when the price does hover back and forth. Near your strike, it can collect back and forth many times, and you can collect. You can be quite profitable that way. So if you do this, can we find a way to link the fees that are collected to the Black-Scholes premium that would normally be predicted or you would find, say, on a trading platform? So to do this, we have to rethink a little bit the type of option that exists. Here, we have an option that expires every block. So it's technically perpetual, but that's because it's renewed every block. So that every block you have to pay a premium if you hold the option. And the key point is that you will only pay if you're near the range that you're deploying. For instance, this is like taking a loan, but the interest rate depends on the price. If your strike is 3,000, the price of ETH at 3,500, you only pay a high interest rate when it's near that area. If it's above, you pay 0. If it's below, you pay 0. So you're accumulating small fees incrementally every block by creating this. So you have to find the price at the end as the sum of all of these tiny increments. We call them the small increment theta. So how can we find theta? I'm going to review this. I'm a physics professor, so I'm going to be going back to my roots of teaching. So if we go back to Black-Scholes model, this was a model described by Merton, Scholes, and Fisher-Black. They were able to describe what the price of an option would be given any time to expiration. Again, options expire in the future. You know that at expiration, they should have a very sharp payoff. You get paid nothing if it's above the strict price. You get paid, or you make money if it's below. But any days from expiration, they were able to extract what the value was. It's a fairly complex expression. You have logs and exponentials, but overall, it's something you can write down. You can analyze. It's not a black box. It's actually very easy to process. So what we do is that if we find theta as the time derivative of the cost of an option, can we recover the cost by integrating theta.dt? So this is the fundamental theorem of calculus. dx dt equals f. Then you can find x as the integral of f dy. So this is what happens here. And if you remember, every time you have a expression, we add up these tiny theta. So here it's taking a continuous solution to this. But then we have to integrate this over the price path. So some price paths can be very complex. They can go to 0 and back to very high. So it's not clear whether it's going to converge to the real price, but you just have to solve this equation for any price path that's stochastic in nature, and that should give you a cost of the option, and hopefully this is going to converge to what Uniswap V3 fees are. So again, the theta, this is the time derivative. If I were to play this movie, you would stay at a fixed strike, and the price would decay over time. So here, from 125 days to 45 to 0, the value decreases until it reaches 0. So if you take the derivative of this expression, it's again, an expression, it's a Gaussian, basically, and you can express it very simply. So now if you take this expression, which is a Gaussian with all known parameters, and integrate it, you can plot, as you make it tighter and tighter, it looks like a very sharply defined Gaussian. And if you're a physicist like me, the closer you are, every block is every 15 seconds. This will be very, very, very pointy. So very high, very narrow. This looks like a delta function for those that like it, that know about it. So you can estimate this. Instead of having this weird Gaussian shape, you can say, aha, this is a square, a rectangle of a fixed width and a fixed height, so that whenever the price crosses that point or that threshold, you just multiply, you just add this k times sigma squared over 2 to the value. Add the small theta that we were describing is given by this expression. And we cannot make it as narrow as we can. We actually make it the tiniest we can be, which is a single tick in most pools. So it could be 1% or 0.3% or 0.05% or even the 0.1%. So here we're limited as to how narrow we can be. That limits also how high that has to be. But if we do this, and now we have a different equation for the premium, we can find that the path that I described before, this one never touched the price. It's cost nothing. So you buy a call option. You hope that it's going to go to the moon. The price tanks. Normally in traditional finance, you have to pay for the option up front. Here, you don't have to pay because it never touched it. You purchased insurance for flood. You never got flooded. You don't pay. It's only when you actually are knee-deep in water that you have to pay the premium. So most options will have zero price, and that's fine. Some of them will have a price that's very close, 85% of Black-Scholes. Some unlucky options will be very expensive, many times more. But if you do millions of simulations, this is a Monte Carlo simulations, millions of simulations, and you look at the distribution, the average price of all of these million possible price paths converge exactly to the Black-Scholes model. So here, we don't know the future, but if we use this expression, we can find that the average premium someone will have to pay will be Black-Scholes exactly. So this is, again, a non-trivial result. And if you look at the two ways to extract option premium on one side, which I just described by having these delta function-like pricing and the liquidity that's accumulated from Uniswap, we actually make them equal now. So we say the price is what the pool has generated in fees. This was a long-winded way to say this is what we assign as being the price. And as long as you were careful with the bookkeeping, the idea is that you compensate the option seller exactly the fees they would collect, but instead of getting the fees by trading, the option buyer will pay the fee at exercise. And it's the same thing when you sell an option. So in the end, the option sellers and the options buyers will get fees that would normally be collected, but it's not going to be their funds. It's not going to be their liquidity. That's going to be the liquidity of the pool. So that's why you can have some leverage. You can control more liquidity than you actually possess. So one key point is the volatility of this expression. This is the IV of an option is very, very difficult to extract. In one of my posts, I do derive on-chain measures of volatility. It depends on the daily volume and the tick liquidity, the liquidity at the currently traded tick. If you do this for most assets, for instance, ETH USDC, the IV is 48%. BTC ETH is 21%. So here, what happens is that the IVs are fairly low. If you go on Deribit or centralized exchanges, the IV would be 100% sometimes. Here, it's very low. So I don't see this as a failure of the model, but rather as a consequence of the fact that we can only sell options now. If you sell, the price is going to go down, the IV is going to go down. If we introduce some way to buy an option, bring up the price, in Panoptic, this is what we'll be able to enable. Buyers will be able to come in, buy options that are underpriced, and remove liquidity, and the denominator will be smaller, the IV will be higher, and hopefully balance will be restored. So that's kind of one way of trusting the market to make the right decision. Right now, someone would make a killing buying options because the IV are so low compared to the realized volatility. So finally, I'm going to complete in the last few minutes how this is also bringing back fungible liquidity to UniV3. So again, liquidity providers will provide funds to the min and max ticks. Not in range, they won't collect fees. They provide them as far away from the current price. But it's going to be the users that will move this liquidity, bringing into play, sell options to bring it close to the price, buy them to bring it far away. And they would have to deploy some liquidity themselves as collateral. For instance, the price increases. At some point, you'll have to pay for it, so you have to have some funds available. But basically, the two roles, options buyer, options sellers, will be distinct from the market maker, which is, again, an LP provider, but the market maker will be handling the liquidity and be paid a fixed commission, for instance. So by the end of the day, even though you start with liquidity all at a min and max, the act of buying and selling options will shape the liquidity profile from something that's now dictated by the market of selling and buying options, as opposed to the LP liquidity providers kind of prediction of where the price is going to be. So that's a different role. The option buyers will be the ones shaping the liquidity and not the LPs. And yeah, so I guess I would just conclude by trying to draw inspiration from Uniswap, and you want to have something that's permissionless, that doesn't necessarily need governance or some ways to dictate which options are going to be available. If you can deploy this contract on any UniV3 pool, then anybody can be an option seller, and then this is a motto from from Cornell University. I would found a protocol where any person can trade options on any asset. And also from a like DeFi moving forward perspective, Theta came in and tried to do an on-chain order book. It didn't work until Uniswap came in and simplified everything for everybody. put the token you want to sell, get the one you want to buy. You want to do something similar. If you don't know anything about options, but you have a TD Ameritrade account, for instance, you log into the account, it's very, very, very opaque and obscure, and it's hard to understand. You can spend weeks just to learn how each one of those numbers work. It looks like a spreadsheet, but it's very difficult to handle. So what we want to do at Panoptic is to have something that's also as simple, streamlined, and perhaps easy to use as Uniswap, in the sense that we can have a more visual representation of the payoff as opposed to just a bunch of numbers on a spreadsheet. So to conclude, I want to thank Advanced Blockchain, Jesper and Max from Advanced Blockchain, Serafim and Matt from Euler Finance that also helped me with some of the pricing models, the Unigrants program and the big brains behind Uniswap V3, and also the Ethereum community and ETH and Denver organizers. So thanks very much, everyone.